So let's see. Well, I hope everybody's getting outside today. Finally, it's cleared up and it looks really beautiful out there. So don't spend all your time indoors. Okay. So I thought what I'd do first before bringing any new material in is just giving a 2-slide summary of what we did the last time, the lecture. So we looked at resistors, capacitors, and inductors, and looked at the voltage and current characteristics. We saw that in a resistor, the current and voltage are in phase, but in capacitors and inductors, they're out of phase, and that depends upon the frequency. There are also frequency-dependent devices, where resistors are not frequency-dependent devices. So someone in the lecture room, can you see my the arrow pointer going around? Great. Okay. Capacitors, inductors only change the flow of current. They do not dissipate energy. They only store energy. Capacitors store energy in the electric field, whereas inductors are just a coil of wire, and in current flowing in a solenoid, a coil of wire produce a magnetic field. So that's what's stored in an inductor. And then we talk about reactance. We talk about impedance and reactance. Well, reactance, how do things react? Well, things can resist changes and not be a resistor. In a capacitor, there's an electric field built up that resists extra charge. And in an inductor, there's a magnetic field which resists extra or changes in current. So these things act like resistors, but they don't dissipate any energy. Well, of course, what you learned in the experiment was, which we'll get to in just a second, that in inductors, a coil of wire, so that thing does have resistance. There are hundreds of turns in the inductor that you use, a very small wire, and that wire has some resistance. So the inductor you use does have some resistance, so it does dissipate some energy. Okay, the LRC circuit. That's a very important thing. We learned about 2 time constants, tau, RC time constant and LR time constant. And we found that you can in a circuit, you can analyze a circuit using impedances. The impedances can be complex numbers. So if you put them in a voltage divider, you can calculate the gain, which is just the voltage on a component versus voltage in. Here's voltage in, say it's a sine wave, and here's voltage of a component that you want to measure. And it's just a ratio of resistances, just like a regular voltage divider. And I thought it was pretty cool that you actually made an LRC circuit and you plotted its gain as a function of frequency. And you found that the gain, even though the input voltage can be, I don't know, say 10 volts, that you can get a peak voltage on the capacitor that's more than that. So that's the issue of resonance. And the resonance occurs at, we call it omega 0, which is 1 over the square root of LC. And that's just when this denominator here and the gain goes to 0, right? When the gain is a maximum roughly when this denominator is the smallest. This denominator is the smallest when omega tau LR is equal to 1 over omega tau RC. So when this thing in the squared brackets here goes to 0, that's when you get the maximum. So this is resonance. It's basically like a swing. We all know, you push somebody in a swing. You push a little kid in a swing. It's a pendulum, right? And a pendulum has a frequency, a natural frequency. And if you push it at the right frequency, the amplitude goes up and up and up as you add a little bit of energy each time. And that's exactly what's happening here. So in the LRC circuit, you're adding energy in on each cycle of the sine wave, but you're also dissipating energy. So at some point, you reach a point where the amount of energy lost is equal to the amount of energy you're putting in, and that's where this peak is. Okay. Very interesting, resonance circuit. And we'll see that a little bit later in what's called a crystal set or a radio. Okay, course hints, good practices. Please review the slides before class. Even if you don't understand the material, if you have a visual of it, then by the time it comes into the lecture class and you see it in lecture, you know that's gonna absorb more in your mind just because you've seen it before. So please try to look at the slides before class, before you come to the lecture. And then review after the lecture, what don't you understand, okay? Because on Mondays, you can join the Zoom and we can, I can try to answer any questions that I can that you have about things that you don't understand, either about the lecture or about the lab experiments. Okay, in the lab instructions, you just think about before you go in, before you look at the video of it, what components will you use, what instruments, what measurements will you make? Try to look at that, not just go into and watch the video, watch me do the experiment and then learn only from that. You don't put, if you put more of your own thinking into it, you'll learn easier, okay? Good practices. Okay. So here we are, the fourth week. We're going to go over semiconductor devices. There's homework of a handout, and then there's worksheet, the last worksheet, and then we'll go into written lab reports after this worksheet. Okay, the stuff we're going to go over today, I think almost no one has much experience with this, unless you've taken a course in, maybe an engineering course or something like that. But we're going to go over semiconductors and the important, the physics behind the devices, physics. So silicon, gallium arsenide, two very important semiconductors. What is doping? When you dope something, you get donors or acceptors. A donor gives you extra electrons, acceptors gives you extra positive charges. We call them holes. Okay. Then if we take different kinds of doped semiconductors and make a p-n junction out of it, you get something called a depletion region. What is a depletion region? What is an energy band gap? We won't go over much about the energy band gap, but mainly about the energy band gap we'll get to when we do optoelectronics, because it's very important when you have light emitters and light detectors. But we'll go over depletion regions. And then we'll go over the bipolar junction transistor and the two circuits that you're going to work on Thursday and Friday in the lab. Okay, what is a semiconductor? What is a p-n junction? How does a diode work? How does a transistor work? What is an amplifier circuit? I'd just like to throw this in. You probably all heard of the Pauli exclusion principle, right? Wolfgang Pauli received the Nobel Prize in 1945. He came up with the exclusion principle: no two electrons can occupy the same quantum state. Okay, it's basically position, energy, and so on. But here's a quote he came up with in 1931. Okay, that was the beginning of quantum mechanics. And this is a quote that I found on the web. "One should not work on semiconductors. That is a filthy mess. Who knows if they really exist?" Okay. We would still be in the dark ages of electronics and basically of communications without electronics and without semiconductor electronics. It's really hard to tell what's in the future. Back then, they were a filthy mess, and it took a lot of technology to be able to refine semiconductors and basically dope them, put them together, and make giant integrated circuits that had a billion transistors on it. Anyway, we've come a long way from that filthy mess. Okay, we went over this once before. You classify materials by the resistivity, the Greek letter rho. And rho is a material property. It's independent of how much stuff you have. Okay, we know a wire has a certain resistance, but copper has a certain resistivity. So that resistivity is the same in copper wire of different sizes, different lengths. Okay, so usually we define metals, conductors, as having very low resistivity, micro ohm centimeter units. On the other hand, an insulator, like glass, ceramic, it has a very high resistivity. You can see 14 orders of magnitude higher resistivity. Okay, somebody came up with the term semiconductor. Okay, it conducts between a conductor and an insulator. And the importance is that not the resistivity isn't the fundamental thing. It's that changes. It's changing because you're doing things to it, but the things you do to it are important. It's not that the resistivity per se is changing, and we'll get to that. So here's just a basic calculation of resistance with resistivity and the length and area of a piece of semiconductor. And I just will put some numbers in. Silicon, if you have a resistivity of 1 ohm centimeters or 1,000th of an ohm centimeter, you get resistances that are 3 orders of magnitude different. Okay, and you can actually make silicon with these different resistivities. Okay, let me point out something here. Notice that I didn't write this number as milliohm centimeters, which you would want to do normally, 1 milliohm centimeters. The reason I wrote it this way is they both have the same unit, so it's really easy to see, this is 1, this is 0.001. So it's easier to see that there's a big difference in them rather than if I would have written 1 ohm centimeter, 1 milliohm centimeter. I think it's just easier to see, easier to spot. Okay, now here we go. Types of semiconductors. There are many types of semiconductors that we've discovered. Of course, the most important one is silicon. Silicon, it has a structure like this. This is the crystal structure. That is, if this were diamond, they would be carbon atoms. And each carbon atom would have 4 what we call nearest neighbors. So it would be called tetrahedrally bonded. It has 4 bonding electrons. And the reason is because it's a group 4 element in the periodic table over here. So all these group 4 elements, silicon, carbon, silicon, germanium, tin, they all have 4 bonding electrons, so that's why they have 4 nearest neighbors, because they're each one of the electrons, bonding electrons it has, is bonding with one of its 4 nearest neighbors. So That's a diamond structure, but if you put silicon instead of carbon in here, you get silicon. Another very important semiconductor is gallium arsenide. It's just called, it has a different name, zinc blende structure, but every other atom is gallium, and then the other atoms are arsenic, so they're half and half. Okay, but notice one thing. You have silicon, nice semiconductor, gallium arsenide, another one. So what you've done is you've taken something like gallium arsenide, gallium over here and arsenic here, a group 3 and a group 5. Well, on the average, they have 4 bonding electrons. The gallium has 3 and the arsenic has 5. So you can make any of the semiconductors as long as they're average of 4. And you can also take like zinc and selenium, a group 2 and a group 6. So as long as you take things that average 4, you can create semiconductors that are pretty much, they have the same structure, but they're just different atoms and they have a lot of different properties. Like silicon, all of our transistors, gallium arsenide, when you want a high frequency, the transmitter in your phone has gallium arsenide in it. If you want to make LEDs, you have to use these other semiconductors. You can't make an LED out of silicon. You have to use group 3-5 semiconductors. We call them group 3-5 semiconductors because you're taking like aluminum, gallium phosphide, things like that. Okay. Anyway, so you can make a lot of different things out of these. Questions so far? Okay. We continue on. Okay,
Chris,
so here's
the chat.
well, yes. I don't see my chat right now. Yeah, can I view the chat?
I can just read it off to you if that's quicker.
Yeah, good. Yeah, please. Okay.
Okay, so the first question is, does that mean that NaCl is considered a semiconductor, or is it only for 2 through 6, group 2 through 6 elements?
Yeah, it's only these. I mean, you can't take. Okay, so something from group 1 and group 7, sodium chloride would be. It has different bonding. It has ionic bonding, and it's different material. I mean, there's a lot of chemistry that goes on. Like silicon dioxide is beach sand, right? So SiO2 is beach sand. Carbon, CO2, is a gas, right? So you can't take anything from here and make this the same materials necessarily. I mean, it turns out that these average of group 4, nature likes to make them in these type of crystal structures, and when they do, they have these certain properties. Yeah. It's complicated chemistry.
And then the second question was, does the makeup of the atom determine its resistivity?
It's resistivity. Well, we'll get to that. Yeah, that's coming up. Okay. A perfect crystal of any of these materials has an infinite resistivity. Okay. Any other questions? Yeah, I don't see my chat. How do you see the chat when you're in full screen? Okay.
I don't think you can see the chat while you're screen sharing.
Yeah, okay. Okay, 4 valence electrons in silicon and germanium. And so here's a silicon. This is a representation of it. And it has these 4 bonding electrons, and they're basically mostly covalently bonded to other silicon atoms and pairs of electrons between the silicons. So as I said, pure silicon, any pure semiconductor has an infinite resistivity. All the electrons are tied up in these bonds, so there's no way to get, if you apply an electric field, there's no way to move an electron. There's no space for it. Even if you take an electron out of one of these bonding places, where do you put it? If you took an electron out of here, you couldn't put it anywhere. So these electrons that create the conduction can't be moved. Okay, to make silicon conduct, make rho finite. Well, you could raise the temperature, but you have to raise it very high, and we wouldn't want to do that. We wouldn't want to raise it to hundreds of degrees Fahrenheit. The way we want to make them conduct is to dope them with other atoms. So you can add a bonding electron or remove a bonding electron. Okay? So you're going to take out a silicon and put in another atom. And I'll show you that concept of doping. So it allows you add mobile charges. You add a small concentration of another atom, like if you take silicon, you remove some fraction of the silicon and put in, say, antimony or phosphorus or one of these. This is a group 5, so this has 1 extra electron, right? It also has 1 extra proton too, but 1 extra electron. So if you dope it with antimony, you take the silicon out, which had 4 valence electrons. You put in antimony, which has 5 valence electrons. So 4 of those antimony electrons go into the bonding, but then there's 1 left over. And this this is mobile, and so it can be moved around. If you put an electric field, battery across a piece of silicon that has antimony in it, then current will flow through it, and it has not infinite resistance. It has some resistivity. Okay, so basically in silicon you could put phosphorus, arsenic, antimony, and nitrogen probably doesn't work too well. Okay, what happens if you put one of these things, group 3, into it? Huh? Think about that. When you take a silicon atom out and you put in, say, aluminum. Okay, you get the concept of a positive charge when you do that. It's a missing electron. Okay. So it's a missing electron. And these holes are what we call itinerant. They're mobile. An analogy of a bubble. I mean, here's a liquid column, and the bubble moves up, right? The bubbles move up because they're lighter density. So you can have the void of something move. So like this hole here can move. Okay, so this hole could this hole here could jump over here and this electron would go away, would move. Okay, so you can get positive holes to move. Let me back up just a second. Okay, so you want this hole to move. Okay, so forget about this free electron here, but suppose there's a hole here, positive charge. To get this hole to move to the right here, you take this electron and you take this electron and pop it over into the hole. So then you're left with a hole here. Okay, so what's happened is the hole has moved from here to here. And you can keep on doing that. You can keep on bouncing the hole from one silicon, one atom to another, and you can get conduction. Okay, so just think of a hole. It's a positive charge, but it's just a missing electron, and they can move just as easily as an electron. Well, not quite as easily. They're a little bit different, but mainly just think of the holes can move basically like electrons. So this is the basis of almost all semiconductor devices. Relies on the ability to make them with excess electrons or holes. Okay, and it's this doping that happens. So that's why you couldn't make them in 1931, because things were so impure, the silicon and other semiconductor, germanium. I mean, there were materials that you can still buy them at hobby stores, but they're probably fairly impure already. But you want to be able to put the right impurities in at the concentration you need. It's technology. Okay. So for electrons or holes, we call them free carriers. They just carry electricity. So when you have extra electrons, you get them from what's called donor impurities. They're donating electrons, and because they're negative, you call them N-type. N-type, N for negative. So donor impurity, and then you have something called acceptor impurity, which donates mobile holes, and because the holes are positive, we call that P-type. Okay, so that's where we get the concept of P-type doping and N-type doping, whether we put donor impurities in or acceptor impurities in. Okay, so as I mentioned before, with silicon you can put any of the group 5 elements to get electrons, or if you want to get holes, you put something from group 3. Okay. Something that you should also be aware of is, okay, you're putting an electron in, right? But think about this is, if I take a piece of silicon that's pure and it's not charged, right? There's the same number of holes as protons. Sorry, electrons and protons. So it's uncharged. So if I put, say, an antimony atom in, it's uncharged. It has, a certain number of protons and the same number of electrons. So when I put that in, you get an extra electron, but still the whole piece of stuff is neutral. So that means that if you created an extra electron, you must have left behind a positively charged atom, an ion. So this antimony is positively charged. All right, because you have to have the balance of charge. Okay. Okay, so now we're going to use p-doping and n-doping to make diodes or transistors or FETs. Questions here? I'm sure this is new stuff to almost everybody. I heard that Northeastern now we're getting rid of wall phones. Okay, if you want to talk to somebody, you know, at Northeastern, if you're faculty or staff or whatever, you're going to have to use Teams. Okay, it's like everything is going to come from our phone now, our cell phone. Any questions about this? I know it's. If you don't have any questions now, think about it and chime in on Monday at the same time, and we'll go over some of these things again. Okay, they're all new concepts. Okay, shall we move on? Semiconductor properties. Okay, we talked about resistivity. Well, conductivity is a reciprocal of resistivity. Carrier density and mobility. And we can, they have these particular units. Like carrier density, it's a density. We usually talk about it. Number of electrons or holes per cubic centimeter. And then we have something called mobility. What's mobility? Mobility is how easily it is for an electric field to move an electron or a hole. And then you have the relations here. The resistivity is equal to 1 over the carrier concentration times the charge on the electron times the mobility. Okay. Here's an example for phosphorus doped silicon. And now when we're doping, we don't need to put many atoms in. Okay, here's an example where I have 10 to the 16th electrons per cubic centimeter. That's the density of phosphorus atoms. So we're only taking out 1 out of every million silicon atoms and replacing them by phosphorus. 1 out of a million. So the density of atoms is about 10 to the 22nd per cubic centimeter. So basically Avogadro's number, close to that. So here we can, if we know what the carrier concentration is, the mobility is, we can calculate the resistivity, and we get something like that. Just a number. But these are typical numbers. And in the advanced lab class, we'll actually measure carrier concentration and mobility of a piece of silicon. So that's in maybe your middler year. Okay, here's a plot. Here's a plot of resistivity versus impurity concentration for phosphorus or boron. And notice, okay, they're both on a log scale. Okay, resistivity and impurity concentration. But notice this, the scale is basically square. It's the size of 1 order of magnitude on the x-axis is the same as the y-axis. So the fact that it's a log-log plot and it's linear means it's a power law. Okay, and this power law has a slope of -1 because the slope is minus 1. So that just says that resistivity and impurity concentration are reciprocal. Okay, so over here on the left down here, resistivity and carrier concentration are reciprocal. Okay, we do this a lot in science and physics and engineering, that we plot things in different ways, and maybe we didn't know this equation to begin with, but we take some data and plot it and say, aha, it looks like a power law. So then we can come up with a model for it. Okay, any questions on that? Okay, now we have N-type and P-type semiconductors, just by fabricating them in different ways. Making them dirty. Basically, we're just trying to make something dirty in a controlled way. Okay, here's the important part. PN junctions. PN junctions are in everything. PN junctions are in transistors. They're in FETs. They're in LEDs. They're in laser diodes. They're in photodiodes. They're in everything. Okay, so let's take two chunks of material that I've doped, one p-type and one n-type. Okay, so that what you see here, let's take the n-type here first. That, remember, the whole thing is neutral, so there's as many electrons, mobile electrons, that's a minus sign here, and positively charged atoms. So as many electrons as there are positively charged atoms. So each one of these things would be like antimony atom. Okay, now look at the p-type material here. And you have mobile holes. And for each mobile hole, you have a negatively charged, say, aluminum atom. So it's an ion. So you have holes and negative ions on this side, and here you have positive ions and electrons on this side. They both start off neutral. Okay. Now we're going to put these things together at an interface. We call it an interface. Okay. So think of what's going to happen. Okay, here you have a hole, positively charged electron that's mobile, electron that's negatively charged. What's going to happen when I have a positive and negative charges that are mobile and they're close together? They're going to attract, right? They're going to attract. And essentially the electron is going to fall into the hole. Okay, and that's exactly what happens. So here, like this electron here will fall into this hole here, leaving behind a positive ion and a negative ion. But you've gotten rid of the mobile carriers. Okay, and that happens all at the interface. So somehow you start off with a conducting material here, and now you have an insulating material at the interface. We call this a depletion region. It's depleted of carriers, and it's an insulator if it doesn't have any carriers. Depletion region. So if you're trying to get current to flow from one side to the other, it has to go through an insulating region. So that's difficult, right? Insulating region. I won't worry about that. Anyway, so there's an insulating barrier here. It's a barrier to conduction. Now here's another picture of it. They only grow to certain widths that are defined because there's diffusion of carriers, and that's offset by the electric field that's built up because there's charges in here. Anyway, I don't want to spend much time on that. Okay, questions. A PN junction. This is the basis of almost all semiconductor electronics.
Professor, I have a quick question.
Mm-hmm.
So in a PN junction, is the reason there's a depletion region because the mobile electron and the mobile hole, like they're obviously attracted to each other, so they they attract each other and they counteract each other. Then is that why there's no carriers in the region?
Right. I mean,
Okay,
when
I'm just sorry. Go.
Yep. Yeah, back here on the left side here, there was a there was a lack of an electron, that's why there's a hole. So if there's a lack of electron, but it's positively charged, so then this electron is attracted to that positive area, and basically it falls into the hole where the hole was. Does that make any sense?
Yeah, I got it. Thank you.
Okay. Any other questions? Okay, remarkable diode action, right? Very first week you measured, you took a diode and you measured the current voltage characteristics. You got a plot like this, where as you increase the voltage here, the current didn't go up until you reached a certain point, and then all of a sudden it went up exponentially. And you plotted it on a log scale so that you could see that it was exponential. And then in the reverse direction, you found that it didn't conduct at all. So it's a one-way valve for current. Positive current flows in the direction of the arrow. Okay. Okay, so here's the crux of how a diode works. Okay, so here's a diode. I'm not putting any voltage on it, no external voltage. And we have this depletion region, that's an insulator. Okay, so if we put a small voltage on it, you know, so this is the p-type region. If you try to put positive here, the holes can't get across this insulating region, okay? But once you get to a certain voltage, see over here on the IV curve, once you get to a certain voltage, you start conducting. And what's happened there is that you're putting positive current in here in the p-type region, so you're putting holes back onto this insulating region. And by the same token, you're getting, because you put holes here, you're attracting electrons over here. So when you put a voltage on it, at some point you've filled up this depletion region back to where it was before you put the two pieces of stuff together. Okay, so when you forward bias it, you're just filling up the holes in electrons in the depletion region. Okay, so now you don't have the insulating region anymore between these two p-type and n-type materials, so electrons can flow. Holes can flow one way, electrons flow the other way. Okay, so this battery, what it's done is close up this depletion region. If you put the battery the other way, it actually removes holes from the depletion region and removes electrons from the depletion region, so the depletion zone gets even bigger. But I mean, it was insulating here, and it's just more insulating here, but still no current flows in either of these directions. So that's why you get this part of on the left, the IV curve, that there's really almost no current flowing here in the reverse direction, only in the forward direction. Okay, so that's the crux of how this diode action works, is you're filling up again the depletion region, the insulating region. Forward bias depletion width reduces, reverse bias depletion width increases. Okay, just trying to give you a picture of what's going on, the phenomenon. Okay, questions?
So basically, by applying a positive charge to the P side and a negative charge to the N side, you're sort of pushing the holes and free electrons to the center, decreasing the depletion zone, and the opposite for when the direction is reversed.
Yes, right. So you for forward biasing, you're putting positive charge here, so you're forcing holes to move away from the yellow region into the white region.
Yeah, because the holes are positively charged, so they'll be repelled by the positive current.
Right. Yeah. So they'll be forced up up in this direction. Right.
Yeah. And then when you flip it, the holes are attracted to the electrons coming in from the negative current, so they pull towards the ends and creating a large depletion zone.
Yeah. So I guess you can think of it there as you're taking holes away.
Yeah.
Taking holes away.
Right. Thank you.
What's happening in the voltage curve on the far left where it breaks down and seems to go to negative infinity?
Yeah, that's there are things also called Zener diodes where all of a sudden there's a breakdown that happens. But in a regular diode like this, you'd have such a large electric field across this barrier here that you'd actually cause like a little lightning bolt to go through from one end to the other, and it would just, ionize lots of stuff and make damage. It basically damaged the semiconductor. If you put 1,000-volt reverse bias on, it would just puncture a hole or several holes in the depletion region and make that conducting. Yeah, so you're damaging it. As an aside, they found out in certain materials, in oxide materials, not semiconductors, but that you could damage a material and then you could reverse it. So you could make a little memory. They're called resistive switching memories. They haven't been a product, but lots of companies have worked on that, resistive switching. Any other questions? Diode action, depletion region, insulating region. Notice that a lot of this course is based on phenomenology. I mean, it's one thing you study something, you have an equation, you're given a problem, you find the equation that has all the variables, you plug in a value and get a number out. Well, okay, that's the math part of it, but what's the phenomenon? What's the physics? Yeah. Okay, let's turn to amplifier. So we have, we'll try to get out of here a little early today. Generic amplifier, 3-terminal device that some output voltage is proportional in some way to the input. And you define a gain as V out, say, divided by V in. I mean, you can have current gain too, current out divided by current in. Okay, and you need things. You need these linear amplifiers for analog devices. You have a little bit of power coming out of your your device here, and you want to get something to a really big speaker that's, you know, putting out 100 watts. So you're going to use a transistor for that. Okay, invention of the transistor, invented at Bell Labs 1947 by three physicists. Okay, they probably built crystal set radios in their youth. Okay, well, their youth was, you know, probably what, 1915 or so. Okay, a crystal set. What is a crystal set? Here's a piece of germanium, and you can, if you put pressure on it, you can make a p-n junction. So here's a coil and here's a capacitor. Where have we seen this before? Right? It's an LRC circuit. It has a resonance. So if you have a big antenna and a ground, you have electromagnetic waves hitting the antenna, a little bit of electricity coming into this. If this LRC circuit, this circuit is tuned to that particular frequency, then you're gonna get a voltage buildup on the capacitor, just like you did in your circuit. Let me spend just a minute on AM radio. So an AM radio means amplitude modulation, and you have a carrier frequency, electromagnetic wave of like a megahertz. But if you vary the amplitude of that, say in 440 hertz, which is a note, A440, then you have a diode here. So here at this point here, you get a voltage like that at a megahertz. The diode cuts off the bottom half of it. Okay, so you only get the positive half. And then the earpiece only reacts to low frequency, so it can't respond to a megahertz. So it only responds to the, say, the A440. So the voltage you get out here, you get a voltage here on the earpiece that's at A440 note, musical note. Do you see any batteries in here? No. This is a way where you could hear a radio station without any power. That what's amazing to me is that with an antenna, a very large antenna, it's picking up electromagnetic waves that are moving the electrons back and forth enough so that you can actually hear it in the earpiece. You have no battery in here. I mean, that tells you that, you know, there's a lot of electromagnetic radiation floating around us and we can't see it at all different frequencies, AM, FM, 1.8 gigahertz, your phone, you know, all these electromagnetic waves floating around and giving energy. Anyway, I mentioned this, the crystal set is, you know, they were making p-n junctions by getting a piece of germanium at their the hobby store and making this. It's ironic that, you know, these guys, I'll bet all of them made, you know, p-n junction diode crystal sets when they were younger. Okay, let's take a little respite here. A 5-minute video. Can you see this? John, can you nod if you can see this?
This doesn't look like
You can't see it?
First transistor.
Oh, okay, hold on.
This replicate.
Okay, stop sharing that. Share this one. Okay.
Is a bit larger than the original.
See it now, John?
Faithful representation.
All right.
In 1947, Walter Bratton at Bell Labs fashioned about a plastic set, a chunk of germanium, and a plastic triangle. On each side of the plastic triangle, there's gold foil. And And then on top there's a spring which presses the apex of the triangle into the germanium. That's why it's called a point contact transistor. Now here's what Bardeen and Bradford actually did with this device. On December 23rd, 1947, they hooked up a microphone to the left side and an oscilloscope to the right side. As they spoke into the microphone, you could see the voice signal being amplified. As Bradford wrote in his lab notebook, the circuit was actually spoken over by switching the device in and out. A distinct gain of speech could be heard and seen on the scope. Now, that amplification is still one of the main uses for a transistor. Think of your cell phone. It detects a low power signal from a cell tower, and then its circuitry amplifies the signal until you can hear it. But how does this klutzy looking contraption work its magic? The key lies in this chunk of semiconducting germanium. Recall there are three ways we can classify material in terms of their ability to conduct electricity. Conductors like metals that readily transport electricity with negative charge carriers. Insulators which refuse to allow current to flow, and a third class which makes possible the transistor, semiconductors. As the name implies, they conduct better than insulators, but not as well as conductors. But more importantly, unlike metals, semiconductors have two different ways to conduct electricity, effectively negative and positive charge carriers. That property lies at the heart of a transistor. It allows an engineer to make a highly reliable device that allows current to flow in only one direction. We can do this by making a sandwich with two types of semiconductors. Here, the negative charge carrier one on the left and the positive one on the right. This semiconductor sandwich allows electricity to flow, reverse the battery, and the current rise to a. Other devices can do this, for example, vacuum, but they have many parts, were unreliable, overheated, and expensive to produce, and likely impossible to miniaturize. This seems a simple thing, yet it lies at the heart of a microelectronics revolution. And it's the key to the Bratton and Bardeen transistor, in fact, with every transistor. It's best to first think of their device as two separate one-way current valves. At the center of each is that piece of germanium, which makes electrical conduct operated. And at the top, a spring presses a thin piece of gold foil into the germanium. Right where the gold touches, there's a thin layer of the positive charge carrier semiconductor. Below that, the rest of the germanium is the negative carrier type. Now, even though that top layer is very thin, I've exaggerated it here to make the operation of the transistor clear. On the left, we attach a small battery with its positive terminal connected to the top layer. This allows current to flow. On the right, we use a larger battery that contains reverse. This creates a device where current doesn't flow. The magic happens when we put the two in contact. The current flows on the left, but because the distance between these gold contacts is less than 2/1000th of an inch, the positive charge carriers in the thin layer are injected into or stolen by the right side. So now current flows there. The current on the right is controlled by that on the left. It seems that we've gone to great lengths to just make a tiny current flow. I mean, the current on the right isn't much bigger than on the left. But if we look carefully, we can see why this revolution.
Professor, we don't have audio anymore. I think it was coming through like your microphone. So if you could just,
Thank you. Okay.
The microphone, see why this
Back up a little bit.
revolutionized the world. It created a signal amplifier. The key element is the battery. Recall that power is current times voltage. So if we use a small battery on the left and a large one on the right, we have a device that amplifies any fluctuations in the current on the left side. These fluctuations might be, for example, the output of the microphone that Bradley and Bardeen used on December 23rd, 1947. Western Electric Company manufactured these point contact transistors in 1951, but they found it difficult to make them reliable, some even showing sudden death. From a manufacturing viewpoint, these transistors have a fatal flaw. They're three-dimensional. As Bratton said, no good physicist likes to work with a complicated case that can be reduced to one dimension. Within a year, Western Electric, Raytheon, RCA, and General Electric offered the junction transistor, a superb one-dimensional device. I'm Bill Hammond, the engineer guy.
Oops. No. Um, Okay, are we back now? Do we have the slides now?
Yep.
Great, okay. There's some other things to look at here about the invention of the transistor. Okay, we call those the bipolar junction transistor. You can have one that's NPN or one that's PNP. Anyway, here's a way to remember that. But basically with a transistor, you have 3 terminals. You have a collector and emitter. That's where most of the current flows. And then you have a base where it controls the current flow. So remember Kirchhoff's current law, right? If this is a node, then the emitter current is equal to the collector current plus the base current. We're not really going to use that. So all the lore of semiconductor transistors say that, okay, a small change in the base current makes a large change in the collector current, okay? I'm going to say, I'm not going to look at it that way. I'm not going to look at it that way. I'm going to look at it and say a voltage on the base narrows or widens the depletion region, allowing more or less current to flow. Okay. So you think of this picture here. You have a depletion region here, and you can change the width of this depletion region by how much base voltage you have. So then you can get current flowing across here, and that changes according to what this depletion region's doing. And this depletion region is governed by the base. So I like to think of this thing in terms of the physics that not in physics, but in the mechanism is you're narrowing or widening the depletion region to get current to flow here. So a little bit of change on the base can create a large change in the basically the resistance across this device. I think of it as a voltage device. Don't think of a transistor as a current amplifier. In practice, think of it as a device where the base voltage controls a transistor resistance. Resistor. Okay, resistance. And then, since it's a resistance device, why don't you put it in a voltage divider? Right? It's a variable resistor, an adjustable resistor. You put it in a voltage divider. I'm not going to show that one. Okay, so you're going to be dealing with 2 different transistor circuits, common emitter circuit and emitter follower circuit. So here's a transistor, just doesn't have the circle around it. The collector, the emitter is always the one with the arrow, and the base is the one where you're controlling the current that flows from the collector to the emitter. Okay, so don't look at this for a while. Just look at, here's a transistor that's resistance can change, and here's a load resistor. So if you can change this resistance, you have a voltage divider here. So this voltage output depends on what this resistance is. And this resistance is controlled by this. So if you put an input voltage here, say a sine wave, you put a capacitor here, which is, it gets rid of the any DC, so it only passes the AC. And then you have another voltage divider here. So you have some voltage bias here, but you have a signal coming in, adding to that voltage bias. It goes through this resistor and it changes this resistance. So then the voltage output you get out of here is proportional to what you're going to put in here. Okay, so there are two voltage dividers in this. This resistor, this transistor is one voltage divider. And then this is a biasing, we call it bias because you're putting a certain voltage in addition to the input. In addition to the input. Okay, so that's one of the circuits you'll look at. The other circuit you'll look at is the emitter follower. So you just take the resistor, the load resistor, and put it down here. So you have the same voltage divider, but just the two components are reversed. Okay. So you're just going to be building this part of the circuit here. This part. So you want a linear amplifier such that a small voltage change in the input makes a larger voltage change in the output. So here they have a gain of 100 that a half a volt change here gives you 50 volt change there. Okay. So the circuit you'll be working with, you'll be looking at linear amplifier circuit and a simple on-off switch. And the on-off switch is what's used in all of your iPhone electronics, all your billions of transistors. So you'll be looking at this circuit, the emitter follower, and there are three regions. This is V-in versus V-out. There's a cutoff range down here where nothing happens for a certain voltage. Then there's a linear range, and then there's a saturated range. I mean, once you get to, I mean, you can't get any more voltage out of here in this V out here. You can't get it any larger than what the battery you put in for the power supply. So that's saturated at some voltage. You can't get any more out. So you're going to build this circuit and look for these three regions. Questions?
So by like V out, is this the voltage drop you have across the transistor?
Right. So if this were a microphone over here, the input, and then this were a speaker here, then whatever you say into the microphone would get amplified in power and be able to drive the speaker so that you could hear sound out of it. So you'd replace this resistor by the end use, which could be a speaker, say.
Okay, so you're like, you have 1 volt go in or whatever, and then like 10 volts potential come out.
Right. Depends on which, what resistor you use here and what resistor you use here. In the experiment this week, you're not going to get much gain out of it. Okay. We just didn't design it that way. You get a little bit of gain, but we're not interested in getting high power out to drive anything. It's just the circuit is just to, look at this plot here. I mean, suppose the microphone here was plus or minus 1 volt. Okay, so if this resistor network gave you a voltage here. This voltage divider gave you a voltage of 5 volts here. And then you had plus or minus 1 volt coming out of the microphone. Then you'd be down here at 5 volts, and the microphone would go up 1 volt or down 1 volt. So if your speech or you're singing a note, musical note, going from 4 to 6 volts up here, it would translate, your 4 volts would translate into 40 volts, and your 6 volts would translate into 60 volts. So as the microphone went plus or minus a volt, the speaker would be plus or minus 20 volts, 10 volts. Would go from 50 to 60 and from 50 to 40. So we'll go from 40 to 60, 20 volts.
All right, so it just kind of amplifies the input voltage by some, and then like by some constant, and then you get an output voltage.
Yeah, you want it to be linear because, well, unless you want distortion. You know, a lot of musicians don't want linear. They want distortion. Jimi Hendrix. You know, a lot of people put their guitar music into a microphone instead of a pickup, so they can get distortion. But anyway, in general, you know, when you have a musical note of A440, you want, you know, A440 over here in the speaker, but you know, not any harmonics of that, say. So this is a case if you don't want distortion. You want to replicate exactly, but just amplify it. Any other questions about this? Okay, that's good. Okay, the bipolar junction transistor. In all of our digital electronics, and even other analog electronics, we don't use a bipolar junction transistor. We use a field effect transistor. Okay, FET. Okay, since transistors are used as resistors in a voltage divider, why not use a resistive device like an FET? Okay, so here's a simple FET, three-terminal device, but instead of base, collector, and emitter, we have gate, source, and drain. Gate, a source, and drain. So the resistance from source to drain is changing as a function of gate voltage. It's a function of gate voltage. And the advantage of an FET is it has very high gate resistance. No current flows into the gate. You're not losing anything coming into here. It doesn't have that threshold like you saw with the transistor circuit. They're simple variable resistors, and you can make them in very small sizes, very high density. That's how you can get nearly 1 billion transistor on a square inch or square centimeter. FET, how does an FET work? Sounds great, right? It's even simpler. And it was patented in 1925, 32 years before they invented the transistor. Okay, it's simpler and it came before, and that's what we're using now. Okay, the gate voltage controls the resistance. Okay, so here's an FET. It's basically saying this one, it's the green is N type, and the orange color here is P type. Okay, so you have p-n junction regions here, so you're going to have a depletion region. So you're going to have depletion regions here. Now, if you apply a voltage, suppose you apply a voltage such that it increases the depletion regions here. So all of a sudden, you have a wide current path in this one. You have a smaller current path in this one. Okay, and if you have a smaller area, say cross-sectional area A, then the resistance goes up. You're trying to squeeze current through a smaller area. And then if you go even further voltage, you can turn off the conduction path completely. That the depletion regions are so wide that they connect and touch each other. So this whole region in here is insulating, and the resistance is very high, basically mega ohms, very mega ohms. Okay, so you see that's you don't have any issues like in a bipolar junction transistor with current flows and so on, but it's just a simple formula that the cross-sectional area and perhaps the length is changing a little bit of the conducting region. And the resistance is changing. It's a simple resistance device controlled by electric field. That's why they call it field effect. It's an electric field that pushes charges one way or another. It's electric field effect. That's why they call it FET, field effect transistor. It sounds a lot simpler, doesn't it? Okay, so we've gone from p-n junction, the bipolar transistor, bipolar junction transistor, to field effect transistor. Now, for modern electronics, we're going to go 2 more steps. I mean, we're still going to use the FET, but we're going to use them in different ways for digital electronics. Okay, something called a MOSFET, metal oxide semiconductor field effect transistor. So it's a field effect transistor, but there's an oxide in it. There's an oxide in it. Okay. This it's a metal oxide, and at the gate is isolated. Okay. So here's the way you draw it here. The gate is not actually electrically attached to the drain and the source. And they do this the following way. So here's a N-type region, a P-type region, and you want to be able to conduct from say the source to the drain, right? You want to conduct through this N-type region. So you put a metal gate on it, but you put a metal oxide. Well, it doesn't really matter if it's a metal oxide or some other insulator. So anyway, but this metal is not electrically contacted to here. But when you apply a voltage to this metal relative to this, you get an electric field here. And the electric field can push electrons or holes away from this region in here. Okay. So it's similar like the diagram before. It's a little bit different geometry. That you want to get conduction from source to drain, and you want the conducting region to vary in size, and you do it with this metal electrode, but the electrode now is insulated from it. So that's why they call it a MOSFET, the oxide, the insulator, an extra insulator. Okay, so what it does is you don't have any current flowing into the gate. If there's an insulator here, you're not going to have any real current flowing through here. So that's an advantage over the standard FET. Okay, want to go one step further? Okay, you're going to take this metal oxide semiconductor and you're going to make it complementary. CMOS. CMOS is all the transistors in your phone are CMOS. Okay, complementary MOSFETs. Almost all the very VLSI, very large scale integration where you have, you know, billion transistors per square inch, square centimeter. And here's how the complementary part works. You have a voltage here and a, you know, a drain and a source here. And you have some input here and you have some output here. And you make two different types of FETs or MOSFETs. One is called a P-type and one is called an N-type. So when they put this little circle here, it means P-type. Without the circle, it's N-type. So if a positive voltage here were to turn this one on, then a negative voltage here would turn this one on. So whatever voltage you have here, one of these things is on and one of them is always off. Okay? So you have a voltage divider, right? So this voltage Q can either be the source voltage or the drain voltage. And one of these things is on and one is off. Or this one is off and this one is on. Okay, so basically no current's always flowing in it. It's only flowing when it changes state. Okay, one FET of the pair is always off. Can draw significantly less power. The power is there only momentarily during switching. Okay, so you have much lower waste heat in CMOS. Because normally, if one of these was a resistor, you'd have some standing current if it was on or off, depending which is on or off. You'd have some resistor here always having current flowing in it, which you don't want. So in CMOS, you only care whether you have in digital electronics, a 0 or a 1, like either source voltage or 0. So this only needs to be, you know, 0 volts or plus 3 volts here. So it only needs to be one of the two states. So this thing is perfect for that. So you put a voltage on here, you get one output like 3 volts. You put the other voltage on here, 0 or 3, and you get the other voltage here. Okay, and you only get current when this thing switches, not when it's in a quiescent state. Brilliant, huh? Voltage divider again and again and again. Most all electronics are voltage dividers. Okay, patented in 1963. Used in microprocessors, microcontrollers, random access memory, other digital logic. Questions? I think we're coming to the end of it here. Yeah, we still have 50 people here. Okay, we've gone from PN junction, bipolar junction transistor, FET, MOSFET, and finally to CMOS. And that's where we are with technology right now. if you've had an engineering class and some kind of electronics, you know, you probably came across, you know, FETs, things like that, but maybe not the physics of how the PN junction works and how it's the basis for all of these devices. If they didn't have CMOS, you'd have to charge your phone every 10 minutes. Well, maybe not 10 minutes, but 8 times more often, basically 8 times more often. Okay, lab hints. Draw the circuit diagram. Arrange the proto board to look like the diagram. Make it look organized. Limit the number of wires. Well, when you get to digital circuits, you're going to have lots and lots of wires. Plot data as you take it. And you can see where you need to take data. If you're in the lab, you can always ask the TA, hey, does this look right? But then Monday, you know, if you're analyzing, writing up your labs, and come to the Zoom on Monday. You can ask questions there. Okay, so we call this hello and goodbye to the transistor, right? It's a good thing to learn from, but we're using FETs. Okay. Any final questions on anything? I see you still in the lecture room there. All right. Okay. Good luck on Thursday and Friday in your labs. I hope as many of you can actually get into the lab as possible. You'll have a lot more fun doing that, I think. Okay.
Professor, when will you be recording?
Yes.
Posting the recorded lecture?
I'll post it soon. Yeah.
Okay.
Yeah. Any other questions? Okay, goodbye. Till Monday.